Hello, I'm Helen, a student from Carnegie Mellon University. I'm here to present our work navigating noisy feedback, enhancing reinforcement learning with error-prone language models. We know that reward design is an essential part for reinforcement learning, and many reward functions are sparse, which causes many challenges to efficient RL. This is because many environments don't have pre-existing dense reward functions, and it is hard to handcraft dense reward functions, since improper rewards can easily lead to inefficient or failed chaining, and also mismatch between chain policies and general test expectations. Also, this process is very time consuming. One common solution to this handcrafting problem is to learn dense reward functions from human preference, which is called RLHF. However, manually ranking thousands of states is labor intensive. To reduce the required human labors, we can use LLMs to complete this process for us since it has strong enough reasoning capabilities. Therefore, we have some method reinforcement learning based on LM feedback, which is called RLAIF. Until now, it's good. However, there is still one critical problem. LMs are imperfect with potentially poor feedback. Since LM ranking errors can reduce the quality of learned reward functions. When LM is uncertain about a ranking over a state pair, it can generate inconsistent state rankings like this figure. When we ask the LM the same question whether state A is better than state B for 4 times, if the LM is not so certain about the answer, it will give opposite answer sometimes. It will give two opposite answers in 4 queries. This kind of inconsistent feedback caused by the low certainty of LM can lead to misleading dense rewards. This will seriously degrade RL performance. So our work focuses on this problem. Our contribution is to propose the potential-based reward functions based on the RLAIF framework, whose scales can naturally reflect an LM's ranking accuracy. Because of this, our method can give uninformative rewards when the LM is uncertain. Therefore, we can avoid misleading rewards and enable efficient chaining, even with small but error-prone LMs. This kind of LM is smaller, faster, and more accessible in practice, so our method has a broader application scenario. Basically, our method consists of 4 steps, including generating pairwise ranking with LM, chaining state scoring model with pairwise ranking, creating a potential-based reward model with chain scoring function. This is our main contribution, and then we can use the reward function to chain policies. In the first step, we first randomly sample consecutive state pairs and then use LM to rank it according to task completion. For example, in this figure, the LM should rank state B higher than state A because in these 2 states, the green agent is moving towards the red target, and state B, the green agent, is closer to the red target. Therefore, the LM should rank state B higher because we should rank according to task completion. And then in the second step, using the ranked state pairs from step 1, we can channel state scoring models sigma s in an RLHF fashion. We use the RLHF loss function to channel this state scoring model. With the state scoring model, we can get a reward function. The traditional RLAIF just uses this state scoring model to score the current state and use the output as rewards. However, our method uses the outputs of the state scoring model as scores the potential of these states, and we compute the potential difference of the current state and last state and use it as the reward. The potential difference intuitively measures the progress increase of the current state compared to the last state. And this method doesn't need any post-processing. The reward function, this reward difference, score difference reward can be directly used in policy training. The potential difference structure is the key to handle noisy LLM feedback with multi-queries. Inconsistent rankings can push potential-based rewards to zero. We can observe this in the formula of RLHF traditional loss. In this formula, we can see that with this negative sign, this loss is just maximizing one of these two score difference term according to the ranking result. If the ranking result is state A ranked higher than state B, and then the loss function will maximize the score difference score of state A minus the score of state B. If the ranking result is the opposite case, it will maximize the opposite score difference. Since we are computing the expectation of this identification function over n query times, we can transform this term into the confidence of ranking results, which is defined as the ratio of times state A ranked higher than state B over n query times. With this transformation, we can see that this traditional RLHF loss function it naturally encodes the confidence of LLM ranking, and it will maximize the score difference with higher ranking confidence because the confidence here is works like a weight for these two opposite score difference terms. And then we can observe this results in a state scoring model training process. When all the ranking results on state A and state B are the same, the state A is always ranked higher than state B. RLHF loss will give state A much higher score than state B. According to this formula here, the confidence here, when the confidence here is much larger than the other one, this score difference will get maximized. However, among these two query times, if two ranking results are opposite to each other, the RLHF loss will maximize these two score difference terms simultaneously, since these two weights are close to each other. Therefore, the loss function will push the scores of these two states close to each other. Then we can get a result like this. At this time, if we use the direct score method, the traditional RLAIF, we will give two states a positive reward. However, the positive state score here doesn't really mean these two states are good for the text. So with the traditional LLM, we will introduce some bias and noises into the policy training due to the uncertainty of LLM. However, with our method, we have a reward of zero for these two states. Therefore, we can avoid the misleading rewards. We tested our method in these three real-world environments and also in several Mujoko environments. Please refer to the results of Mujoko environments in the paper. Here we just show the results from mini-grid. And we compare our method with two baselines, including direct rewards, the traditional RLAIF, and also default rewards from these two environment documentation. In the first experiment, we tested our single query potential-based rewards. The result is the policy learning curves from three environments. Each row shows the results from one environment, and each column is the result with one ranking method. The GT here means the ground truth ranking, which is the human heuristic ranking. Now we also have results with the GPT-4 and Llama 3 here. And our method is shown with this blue curve. We can see that it learns fastest, achieves highest returns with this variance. In the second experiment, we tested the multi-query potential-based rewards. We first synthesized multi-query dataset to test it so that we can see how much improvement our method can achieve for each kind of ranking accuracy. And for each kind of ranking accuracy, how many queries are required by our method to achieve the optimal policy. The first row is the policy learning curves with our method, and the second row is with the traditional LLAIF. We can see that no matter how many query times we use, the traditional LLAIF cannot then use for policy with these ranking errors. With our method, as long as we use enough query times, even if we have 60% ranking accuracy, which is closer to random guessing, we can still learn the optimal policy. And also with higher ranking accuracy, the fewer query times our method will need. In the third experiment, we tested our method with the real LM dataset. We used the 5-query mixture data, and our method potential-based 5-query reward is shown with this blue curve. We can see that the blue curve always learns fastest, reaches highest training return with this variance. Then potential difference 1 query, direct reward 5 for 1 query. And we also show our method is less sensitive to values of step penalty. Here we show different the values of step penalty, the policy learning curves with different values of step penalty. Step penalty is a common method to solve rewards hacking problem. The traditional LLAIF also needs it. And we can see that with the traditional RLAIF, we need to carefully tune the value of this step penalty, and the direct reward can easily fail with some small step penalty. However, with our method, you can always learn some useful policies with whatever value of this step penalty. As a conclusion, our work incorporates noisy LM feedback into reinforcement learning. It learns a potential-based reward function over repeated LM rankings and issues uninformative rewards for states where the LM is uncertain. Thank you for your listening.